Now we turn our attention to a different way of understanding mechanics, which is related to the Newtonian way, but complementary to it, and gives us the basis of something which is underlying a lot of not only physics, but chemistry and biology, something called energy. And today we'll describe what's called the basic energy model, at least by your textbook, although I haven't heard it used by many other people. It turns out that it's extremely difficult to define energy. Many textbooks define energy as the ability to do work, and then define work as a transfer of energy. That's obviously circular and not too useful. A possible mental model is to think of energy as the currency of the universe, the money which the universe spends to get things done. Like money, energy has multiple forms, and moving energy from one account to another account can allow things to happen. So if you think about the way things work in the human world, that people have wealth, but it's really only in transferring wealth from one place to another or from one person to another that things happen. That if you have all the money in the world, then you're not really rich because you can't do anything with it until you spend it. Likewise, energy is this thing related to the state of a system, and transforming or transferring the energy allows you to change the state and affect the physical world. Whenever talking about energy, it's crucial to define and keep in mind the system being discussed. A system is a mental collection of physical objects. It can be as simple as one object, such as Alice, or it can be as complicated as you can imagine, such as 100 billion individual stars in the Milky Way. Much like reference frames, the choice of system is arbitrary. You pick one that makes logical sense or helps you solve problems. Throughout this chapter, we'll get some practice in picking systems to be useful. The basic properties of a system, and this is straight from the AP people, is that 1, a system is defined as either an object or as a collection of objects, but the objects themselves are each treated as having no internal structure. So we might say that you have a school bus full of students, and the bus is the system, and the students are the objects, but we don't worry that the students themselves, of course, have a bunch of hearts and bones and muscle and brain. We would neglect those, right? We'd say that the students are the object and the bus is the collection of them. Or a class of students may be even better, partly because the system itself is not a physical thing. So if we think we have a class of students, it's this mental grouping of a bunch of individual students. Interactions can occur between different objects in the same system or between objects in different systems. And interactions occur in two ways. A force can be exerted between objects in the same system or between objects in different systems. Or there can be a transfer or exchange of some quantity between objects in the system or with objects outside the system. I know it's a little fuzzy and it will get a little better as we go on, but basically we're saying that you can interact by either exerting a force or by actually changing the quantity of something. Any system can be classified as one of the following. It can be open or closed or isolated. An open system allows matter and energy to enter or leave the system. A closed system does not allow matter to enter or leave the system, but does allow energy to enter or leave the system. And an isolated system allows neither matter nor energy to enter or to leave the system. I tried to make that a little bit more concise in this little chart over here, but we're basically saying from open to isolated is getting more and more restrictive on how it interacts with the outside world. Sometimes called the environment, and you'll hear me saying that. We haven't actually defined energy yet, you've probably noticed that, so for now our main focus is on the transfer of matter into or out of a system. So let's do an example here. Let's say that we have a mug full of coffee. So here is our mug, and we've filled it with coffee, which is disturbingly blue. Maybe we'll make it not blue. Oops. There's our coffee. This system is open because you could, in principle, sprinkle in some sugar or some cream or something. And so you could add matter to the system. Or you could take a drink of it and take coffee out of the system. Also, of course, the mug is going to cool down with time. The coffee inside is going to get colder as it radiates heat back out into the environment. Consider the same thing, but now let's talk about we put a lid on our coffee mug. Maybe this is a thing you get from Starbucks or whatever. Now it's a closed system. You can't add anything in, you can't take anything out. You can't drink from it, you can't put in cream, you can't put in sugar, nothing. So there's no matter transfer, but it still allows energy transfer. It's a closed system because the mug will still get cooler. The coffee inside will get cooler as time goes on, as it radiates heat. And then finally, imagine you have instead a thermos, one of those like travel mugs, if you prefer. And inside the travel mug is some coffee. This is an isolated system. Well, at least approximately. It's isolated because matter can't enter and close. It's closest to matter. Matter can't get in or out. You can't drink it. You can't add anything to the coffee. But it's also, if the thermos is well insulated, heat won't get in and out. It will retain its heat for a very long time. If it was truly perfectly insulated, it would retain it forever. Real systems, of course, aren't perfectly insulating. So really, this would be a closed system, but it'd be a very weakly closed system because it'd be almost isolated. And we'll often do things where we assume ideal cases, and it is isolated. It's important to remember the choice of what constitutes the system is up to you. There is no right answer, although there's often convenient choices. You pick your system to make your life easier, based on what problem you're trying to solve. And your choice, of course, affects whether the system is open or closed or isolated. For instance, if the system was a mug full of coffee, and then you mixed in some sugar into the coffee, that would make it, that system is open, because we're adding something to our system, which is mug full of coffee. But if your system was a mug full of coffee and a packet of sugar, that's a closed system, because now the sugar, which is already inside, is being added in, and you're not allowing anything else to come into your system. You're not allowed to add anything to be added in, or in this case, taken out. Example. A diver uses a springboard to dive into a pool. Consider the moment the springboard begins to relax until the moment the diver is at her maximum height, and neglect air resistance. Which of the following would be considered a closed system? Well, we have, obviously the diver is involved, right? But we also have to worry about things like the springboard, which is in our system. If we want the system to be closed, we want nothing entering or leaving our system. So we want to include the springboard, which tells us the way they've rigged this, that it would have to then be all of them, because it's the only one where the diver and the springboard both appear. And we should include the earth because, in fact, there'll be interactions with the earth, and we'll see later we don't want that coming in or out.